In this video, I'm going to be describing what you'll do for Experiment 7, which is the gas laws experiment. This is a discovery lab where you're going to be determining the relationships between pressure, moles, temperature, and volume, which are the simple gas laws, and you're going to be doing this experimentally and graphically. So in part A, we're determining the relationship between pressure and volume, and you're going to start with a syringe and you'll set it to 16 milliliters, and you're going to squeeze that syringe with a pressure gauge attached to different volumes and then see what happens to the pressure at those volumes. So for example, let's say you did a couple trials and the first time you squeezed your syringe to a volume of 14 mils, the second time you reset it and set it to a volume of 12 milliliters. The actual volume in the syringe is what you measured plus 4 milliliters, and this accounts for the space between the syringe barrel and the pressure gauge, because we have a piece of tubing set up between our syringe. Sorry for the not great artwork, but anyway, you have a piece of tubing set up that connects your syringe with your pressure gauge. And so we have to account for this gap by adding those 4 milliliters. And this is what we will put on our plot. So once you have those numbers, you will also, at the same time you squeeze the syringe to get to a certain volume, you'll also see what the pressure gauge is indicating. So for this one, we'll write down 50, and for this one, I had measured 155 millimeters of mercury. To get the actual pressure, we have to account for the pressure of the atmosphere, so the atmospheric pressure. For this experiment, I had measured 756 millimeters of mercury, but you will record the pressure either from the barometer in the laboratory or from what your instructor has measured and put on the board. So in order to get the total pressure, we'll add what we have on the gauge plus the atmospheric pressure. So this gives us 806 millimeters of mercury for our first data point and 911 millimeters of mercury for our second data point. We also want the inverse of the total pressure because we're going to be preparing two graphs to see what the relationship is between pressure and volume. You can do this in Excel simply by typing equals 1 over 806, and it will calculate this number for you. You can also do this on your calculator so that you get a decimal value. Sometimes Excel will rewrite this in scientific notation, so you might also see something like 1.24 E minus 3, and what this means is 1.24 times 10 to the negative third. So don't be alarmed by this notation. This is perfectly normal. It's just Excel's way of using scientific notation. And we can do this for all of our data points, just 1 over our total pressure. You can even type in the cell if you are comfortable with Excel. And again, we would get a number like 0.00110. In Excel, this would look like 1.1 e to the negative 3. Excel also likes to cut off zeros at the end of a number, so if it's giving you the wrong number of sig figs, you can always fix this by formatting your cells appropriately. And there's instructions in your Excel guide for how to format your numbers, make sure you have correct sig figs, do this graphing correctly. All of that is available to you. So we're going to make two plots for this experiment. One where we have the total pressure versus the volume, and one where we have the inverse total pressure versus the volume. And your job is to determine which is linear. Both of them may look kind of linear, but if you zoom in on your data by changing the axes, you'll be able to see which one is actually linear. Usually the r-squared value may help with this. And the one that's linear will get a trend line. So make sure that you add a trend line to your linear plot. Then we'll move on to part B, which is Charles' law. So with Charles' law, we're investigating the relationship between temperature and volume. We are making two plots because we want to know whether it's temperature in Kelvin or temperature in Celsius that has a direct relationship with the volume. So with both of these plots, we're plotting temperature on the y-axis, volume on the x-axis, and your job is to see that both of them will actually be linear, but in this one, we're going to be judging our relationship based on the intercept. So one graph will have an intercept close to 0. The other graph will have an intercept that's going to be close to 273.15. And the one that's 0 is the one that has a direct relationship. And that's what we want to investigate. So you will make both of these plots and investigate which is the direct relationship, whether it's Kelvin or Celsius. Then in part C, we investigate the relationship between moles and volume. So in this experiment, what we're going to be doing is actually performing a reaction and seeing the relationship between the moles of gas evolved and the volume of gas that's generated. So the reaction is fairly straightforward. It's a gas evolution reaction, also an acid-base reaction. And so we have sodium that's going to pick up and form sodium chloride. And the other product is carbonic acid, which we know breaks down into water and carbon dioxide gas. And so we will see the reaction bubbling as we perform it in the syringe. And we're going to measure the volume of the CO2 bubbles that are formed. So to set up the reaction, you'll set it up for 5 different runs, and you'll obtain different masses, or a range of masses. So I'll put range so that you remember. If you don't use a range of masses of the sodium bicarbonate, you'll get one and the same point on your plot. So you want to make sure that you have 5 different values ranging from 0.03, which is kind of the smallest you should go so that it'll expand the syringe. And don't go above 0.15 because you'll completely fill the syringe and then you'll have to repeat that step. Once you write down the masses, you'll measure out your sodium bicarbonate and you'll add hydrochloric acid in solution to your syringe, and you'll cap and shake the syringe. And before you cap and shake it, before you shake it up, you will want to measure the syringe volume. So this is after you add your HCl and cap it, you'll measure the initial. Then you'll allow the reaction to happen and you'll have your after shaking, and that will be the final syringe volume. So the volume of CO2 evolved will be the final minus the initial. So these will be measured in the experiment, as well as the mass. Everything else will be calculated. So we'll calculate moles of sodium bicarbonate by converting grams to moles using the molar mass. So we'll divide by the molar mass of sodium bicarbonate for each one. So we'll do that down the line. You can have Excel do this calculation for you. All you would have to do is type equals and the number that you have for your mass or your cell if you don't include the gram unit, and you would just divide your cell by the molar mass, which is 84.008 grams. And then you can highlight that all the way down. The moles of CO2, if you look at the balanced equation, there is a 1-to-1 mole ratio between the carbon dioxide formed and the sodium bicarbonate. So these two columns right here have the same values. So you can just copy them right over. It's the same number. And that's why we chose a 1-to-1 reaction. And then when you do the final minus initial in your last column, then you can prepare your plot. So you will take the moles and the volume and prepare a plot. Notice we switch the axes on this graph. Then you will add a trend line and see the relationship is going to be a linear relationship or a direct relationship between moles and volume of gas. One more thing in this part, so we may ask you to relate the volume of the syringe barrel with the amount of sodium bicarbonate used. So this is one of your questions. So notice that the plot, the things that it relates are volume of CO2 with the moles of CO2. And you can see that sodium bicarbonate is not a direct thing that you can get by using the plot. However, if you know the volume of CO2, you can use the trend line to solve for the moles of CO2. So this is something we can do with our trend line. You would plug in a value for y, use y equals mx plus b, and be able to solve for your x value, which is the moles of CO2. Once you have the moles of CO2, you can just set up some stoichiometry to solve for the moles of NaHCO3 because we know that they react in a 1-to-1 mole ratio. And once you do that, you can use the molar mass of sodium bicarbonate to figure out what mass would need to be used in this reaction. And so the molar mass of sodium bicarbonate is what we used in the table. Just want to verify, 84.008 grams per mole, which is what we had above. And so this would allow you to solve for the grams of NaHCO3 in the question. Have fun!